Anything? Yeah, I don't have anything. That's cool.
Hello, people in the future.
People in the future. Okay, so let's go through the explanation to Marinho. So what we are doing. So there is a function called search, and this function will call the other two functions. And this is the function that is actually the implementation of a SQL select. So right now we're gonna assume that you want a specific key. So like when you have SQL, you're gonna do something like select blah from blah where blah equals blah. So right now we are hard coding this to only a name, a single keyword. So this is what it's one of these two. I don't remember which one.
It's the first.
Yeah, so it's the first. So what we are doing, we are basically building pages and doing using that to do the search, and throughout that process, we are using the b plus tree. That's basically what's happening. So if you take a look, this function in this line here, it's calling build pagination.
Do
And
you want me to give a overview of the idea? I think it's easier than speaking in terms of the functions.
do you think you can do that with some visualization, maybe on in Emacs?
I can. I can.
I think that's the best way ever to explain.
Let me think of something here. Just a sec, because I need to just close my work stuff or just not share it at
Yeah.
least.
So, but just to finish the thought, build pagination calls build pages. So then I
Uh,
decided to go bottom up last session, and then I decided to we focus on translating this.
can you guys see?
Um, yes, I can see your screen.
Yes.
I'm watching Lemos watching Magetta.
And
So
I'm watching myself on Twitch, so I'm watching myself watching you watching me.
that's deep. I'm sure that's something Confucius would say. So, do you guys know the difference between a B plus and a B3?
I always forget.
I do actually. I do
Okay,
actually.
so please go ahead.
Right. So the main difference is that in a regular B tree, you have the keys and the values in both the leaves and the branches.
Hmm.
While in a B plus tree, you only have the keys in the branches, which you need to do the lookup, but all the
Hmm.
values are at the leaves. And
And
Ah.
additionally,
and what does that
and
give you?
additionally, that gives you that gives you more predictable performance, and also it allows you to have all the data living somewhere else, not
Oh, that
necessarily in
gives you
memory.
ordering, right?
Yeah, the keys give you ordering. That's not specific to like B plus trees. B trees,
Yeah,
regular B
but
trees, do have
yes,
ordering. It's just
the idea is just efficient access, right, by indexing.
yes,
But it also one of the bonuses that we get is that things are ordered, right? So we can just access a linked list, which is like the file, but ordered. So it's a representation of what is on the file, but in a logical ordering. So it doesn't need to be ordered in the file, so it can be dissociated from it. You see? So
I
let's
see.
make an example here. So let's suppose, okay, let's think of this. The main process in the beginning, I think it's worth repeating this. We write things in a sequence, right? So
Yes.
somebody comes there and says, okay, insert this for me. And then you insert a row, and then you serialize, insert another, and so on. And then in the end, you have like 100, right?
Yes.
And then you say, okay, search for me one person in this, like, imagine two columns, like name and age. Select
Mhm.
me for me people who have who are who are greater than 18 years old. I don't know, driving license, 16, right? Whatever.
Yeah.
Um, so for you to do that search, you have two options. You have the naive option, which is the one that we are going to have to default to if we fail on the others, which is doing serial search, right?
Yes.
So you have to go necessarily from, depending on the query, you have necessarily to go from the beginning to the end for you to get the correct result, right?
Mhm.
Right,
Um,
right.
if it's a unique key, like a primary key, or what I call an ontological key, uh, that is the key that gives the meaning to this row to exist, then you can rely on the idea that it's unique. So it should be basically, if you find it, you can just short circuit. You can prune the tree search, right?
Yeah.
Right.
So, but those are essentially the two things. Like you have to always go from the beginning to the end, but in some cases you don't need to do that. So let's think of this. When we are writing to disk, we're gonna write things in a sequence, and then we have a thing called let me show here. Microsoft SQL Server Index. I think here, this documentation is pretty good. Okay, so we have different kinds of indexes, right? We can have, and you can see like some databases, they have a lot. So I'll just go over some of them, okay?
Sure.
And then we see which one, and then you guys tell me which one we're doing here. So
Okay.
a hash index is, with a hash index, data is accessed through an in-memory hash table, okay?
Yes.
Hash indexes consume a fixed amount of memory, which is a function of the bucket count. So basically just keeps track of the where this thing is at, right? So you just search by the index, like the age. So you would have a age and then offset, right? And then you say, okay, I want to find the age X. And then you just go to the hash table, run the function, the hash function, and then you just get the thing, right?
Mm-hmm.
That's
Right.
pretty easy. Memory optimized non clustered. Okay. For memory optimized non clustered indexes, memory consumption is a function of the row count and the size of the index key columns. Okay, but what is a non clustered? Let's go here. A non clustered index can be defined on a table or view with a clustered index or on a heap. Each index row, so pay attention to this, each index row in the non-clustered index contains the non-clustered key value and a row locator, so an offset. This locator points to the data row in the clustered index or heap having the key value. The rows in the index are stored in an order in the order of the index values. So this is important. But the data rows are not guaranteed to be in the particular order unless a clustered index is created on the table. Okay? So what is a
Jeez.
clustered index? A clustered index sorts and stores the data rows in a table or view in order based on the clustered index key. The clustered index is implemented as a B-tree index structure that supports fast retrieval of the rows based on their clustered index key values. So, okay, what's the difference between these? Can somebody
My
summarize?
understanding is that the non-clustered only gives you the ordering property on the keys level, and
Yes.
the clustered one gives you on both the keys and this data.
Which one we are doing here?
Um, I think that we are doing clustered,
We're doing non-clustered
non-clustered, because you said
because
that in
we're
the B plus tree we it gives us ordering.
yes, but but that's on read, right? That's not on write.
Ah,
It's on read, and importantly, it's only on the keys. That's the very definition
Yes,
of
and it's only on the
clustered.
key. So yeah, it's memory, right? It's not it's just the memory time. It's not the storage, the disk, right? That's the main distinction. There's more stuff like if you guys want, you guys can read this. There's a lot of good stuff here, by the way. Like for example, one that I completely uh got like, what the heck is this spatial? You can search by like spatial objects. You can store coordinates and do searches based on like polygons. It's really interesting.
wow, that's fancy.
Yeah, they have this geometry type. It's for like maps and stuff,
It
Uh,
would be very useful for an MMO map
yeah, yeah, this would
implementation.
it would. Man, like XML is pretty interesting as well. Um,
Yeah, I think we're
I
gonna do
think
the
on
game in the XML, right?
yeah, absolutely. But I think also Postgres they allow blobs, like you can index like binaries. I don't know about arbitrary binaries, but some of them you can.
Okay, I have a
And
question. So we are
mhm,
doing non-clustered
mhm.
because we only have the ordering of the keys. The data is actually, whatever order. Is that what I
In rough
understood?
terms, yes. I mean, there's more to that. We don't have the notion of a heap and so on, but uh, basically that's the idea. Like we're just abstracting that on read. That's the point.
Yeah. Okay.
So okay.
Okay.
So
Okay.
what
Now I
would
have
we
another
do?
question.
Okay.
Marinho said that the difference between a B tree and a B plus is
Mhm.
that in the branches we only in the B plus in the branches you only hold the keys and the data is actually only on the leaves.
Yes.
Why is that good for us? Can you
Okay.
can you
Let,
explain
let
that?
me explain the process and then you will see with any example. I think it will be easier.
Sure.
Uh,
Uh, any question, Maria?
no, I was just gonna say, if you have to have the data on the branches, that kind of makes it harder to like it makes it harder to have data that lives elsewhere, not necessarily in memory together with like alongside the tree.
I don't think I
And
got that.
and it also makes the search like searching the value associated with a key, it makes it less efficient as well, because at each at each point you may have to stop your search at an arbitrary depth of the tree instead of always going all the way to the leaves. It becomes more
Oh, okay, that
predictable
makes
that way.
sense. That makes sense. But go on, Mageta. But I'm gonna keep that what Marinho said in mind.
So okay, I'll explain the whole flow, right? So basically, think of this: we have the things stored arbitrarily in the disk, and then we need to retrieve that information at some point in the future.
Yeah.
So what we have to do with the data we have at hand, right? So one option would be to build a hash table. We're not going to do that now, but that's a valid option as well. Uh, so think of this: you have a query that says something like select star from uh, table X where table X dot value whatever uh, equals 3, right? So you're comparing. So you have a function, a predicate, basically saying, okay, this thing here is needs to be equals to this, right? Equals to 3, whatever. If it's an integer. So what we have to do is convert that to a actual predicate, right? And we can do that like I kind of did that in F sharp. We abstract that in Racket later. And then what we do is that we need to paginate, because if you have like 1 petabyte in the disk, you
You
can't
don't have. Yeah.
you don't have enough memory to load all of this,
Yeah,
right?
that part I got
Nor you
it. The
want
reason
to.
that we need pagination is because the data that we are storing, we cannot have it everything loaded in memory. That makes total
Yeah.
sense. That makes total
And
sense.
you asked a good question last time, saying why don't you rely on the operating system to paginate a file for you? And
Oh yeah, he mentioned that. He mentioned that.
that's a good question because you can, like, I think SQL Server it kind of does it to some extent, for example, but
Really?
you cannot do that 100% because you still need to add metadata for that. So you would just benefit from the read and write of the OS, and you're locking yourself. Like some databases, as crazy as it may sound, they make their own file system because of that.
Yeah, that's just
Uh,
extreme.
yeah. So for example, NTFS on Windows basically uses a version like of SQL Server like to do search. So that's pretty interesting to think about. Um,
Um, it's not that crazy to implement your own file system in the DB, because if you think about it, The file system itself is basically a very rudimentary DB.
Yeah,
Yeah,
it
no,
is.
yeah,
Yeah.
no, yeah. I'm just saying
Uh,
it's going to
the only
extremes.
problem with
Like,
that, you have some benefits, but you also have some downsides, right? One of them is certainly portability. Like if you have to port your database to another OS, you have to adapt the file system to the system calls, right?
yeah,
Uh,
that makes
so
sense.
that's one problem. But anyway, okay, so with that out of the way, I think we can go on the meat of the problem. So imagine like this: we have the search, the predicate, right? And then we have this pagination that we're gonna read in portions, right? So we're gonna read the, I don't know, in chunks of like, let's say 1 gigabyte, and you can read 512 megabytes at one time, at once, right? So you just read that chunk and then you read twice, right? You read
Yes.
the first part and then you a window, and then you read the second part, and that's it. So of course this is just a stupid problem. You would like have way smaller pages, right? I think I'm using 8K, I think.
Yeah, we didn't go to that part yet in the Racket, but
Yeah, okay.
I remember
But
it's
anyway,
8K.
that's
Yes.
like an arbitrary number. You can have well, depending on the DB, they set that for reasons, but whatever. For our purposes, this will be totally arbitrary. Um, and then what we end up doing is that we need to window over. So ignore this windowing. Okay, focus on only one chunk. So you read this chunk. How do you search things for this chunk?
Man, how the heck are we gonna test that? Like, are we gonna have to include CSV parsing so we can have a database from the internet?
I didn't get the question. What do you
Yeah,
mean?
because I'm thinking, okay, this is completely arbitrary, but it would be nice to see, like, to try to test with some significant amount of data, like,
Mhm.
and then that's easy to find on the
Oh, I
internet. You can
see. Like
find
to
public
insert and read
databases.
it back, right? True. You
Yeah,
want to do
exactly.
some kind of benchmark, right?
Yeah,
Something like
yeah.
that.
So then there's plenty of available data sets in that you can find in the web.
No, we
S-
can do something like import, like PG copy, like something like that.
Yeah,
We
yeah,
can do
but I'm
this.
thinking, what are the requirements to make that happen? Definitely parsing CSV.
Yeah, which is you can
It
already do in
yeah,
Racket
this
actually.
should be like a piece of cake for something with this amount of libraries.
Hmm.
I know
So
how to do that because I had to do like the first version of my work time calculator, the timetable program I have on a gist. The first version was written in Racket, and I used the CSV parsing library, so I know how to do that. If you know, it's not hard. I mean, it's CSV. If it's CSV and it's hard, you're doing something wrong. But
yeah, but
I did that
that's
already.
only a thought that I want to throw in here because I think that what Mageta is saying that it's completely arbitrary 8K. Maybe you're gonna discover that it's not. Like,
No, I mean, on our case, I don't see a reason why, but it's not arbitrary. Like people do that for reasons. But
yeah. Okay. Anyway, go on.
so, where did I stop? Okay, so imagine you're reading just one chunk, okay, and then we can abstract for two chunks later.
Yeah.
That's not a problem.
Yeah.
So you have one chunk and divided into multiple pages of 8K, right? So you
Yeah.
have 512 that you can load in memory at once, and and then you have like, I don't know, 10K per uh, page, right? So you can store 10K per page. So you can have 512 pages, right?
Mhm.
Uh, Wait, I said megabytes, right? Whatever. Anyway, you got the idea. We're gonna have like a just a chunk per the page,
Yeah,
but
we're slicing the data. That's fine.
yeah, yeah. So with that, you need to build the indexing on that. So the indexing would be like a column that you have specified in your schema, and you can persist the indexing depending on it. Like for example, the hash, it certainly persists. um, or we can build the index and on demand, which is what we're doing, which is a
Yes.
naive approach,
Which is
but
what
I
we're
think
doing.
it's a baby steps. Right?
Yeah, baby steps.
So,
Baby steps.
so what we're gonna do is read the index. Sorry, read what index we should build upon. Right? Build
Yes.
the build a B tree based on that, and then it's going to be sorted on the leaves, and the access will be easy by the predicate that we have to compare with the intermediary nodes of the tree. So let's say in this case, you have like 5, 4, 6, and then you add 3, you see?
Yes.
And then I'll just add, oh, I will add 7, and then I will add 8. So basically, we can now say, okay, it's I want to search by 5, and then I say, is 5 greater or equal than this? It's not. So
We can't
it's
see your
less.
mouse, but I
So
think you are pointing to the 6.
wait, you can't see my mouse? What the heck?
Yes. I'm not seeing. Can you see his Mageta's mouse, Mari?
I cannot actually.
What
I
the
didn't
heck?
even notice.
Now we can see. Now we
What?
can see. Now it is in there.
This makes no sense,
No, no,
man.
no.
What?
Wait. It was in there. It was in there for a
No,
moment.
wait. You guys can only see my mouse if I go to Discord. What
Yeah.
the
Oh, well,
heck?
yeah. Okay. Okay. So then that explains what's happening.
That's bizarre. Anyway, I'm sorry, guys. I can't share everything because I have work stuff, so
That's
I'll
no,
have
but
to do this.
but just be more precise with what you said. So
Yeah, yeah. Let me
is
put
it greater
Discord
than
on the other
6?
side. No, I'll do a trick here.
I don't think the trick that you are thinking it's possible, but that's good. Let's try.
Yeah, I don't think so. Oh yeah, it is. Okay, so imagine this. Sorry, I'm using Discord in reference. So,
Yeah,
uh,
that's crazy.
so we have 6 here, right? So
Yeah,
I want to find 3. So you say, okay, it's less. Then you go here. Oh, is it less than this? Which number is this? I don't know.
5.
5. So it's less than 5, yes. And then boom, you got it.
Yes.
And if you didn't get it, you just keep going, and then until you find in a page, right? It will be in the middle. Like let's
Oh, okay.
suppose
So
you,
the B plus is basically a shortcut.
yes,
Okay, okay. That
and then
explains everything now.
and then the point is you can read in a sequence if you want.
And we are indexing based on the field that you asked for.
Exactly. So for now we're
Ah.
not building, we're not persisting the index, right? We should, because that most of the problem here is like building the index. That's why we serialize twice, right? It's kind of expensive.
But how do you know, like, oh, every time a new row comes in,
You just
the B
you
plus
just
tree will do the
insert.
trick anyway?
Yes, sir.
But wouldn't that change? Wouldn't that change previous indexing?
Well, yes, but what's the problem?
Because you're gonna have to persist everything again. Like, let's suppose that we have this tree that
Oh, you're
is on the
saying you
screen.
have to run everything on the tree again?
No, you're gonna have to go through all the table data, which is with the
Hmm.
fields already indexed, and double check if the index should be updated or not.
No, it remains the same. Let me give you an example here. So let me clear this, and I'll insert big numbers so we can put things in between. So 100, then 200, then 300, then 400. So this is more or less the case we had, right?
Yeah.
Let's just stop here. So it will be split in 2 levels here. So okay. And then you say, okay, what's the use case you're saying? We add a new thing in the middle, right?
Yeah. Yeah.
So a key like, I don't know, 250, right?
Yes.
250. That's the same. This is the index.
Wait, what is the index?
This.
Uh,
These intermediary nodes are the index. They did not change.
yeah, but what if you create like a third level by adding more data?
Okay, so that will not change either. Like 270, it will expand this guy. And then if you put 280,
Yeah, but the 250 no, but the 250 is now in the different level. You see?
well, 250, the 200 is on the same level. You just have another.
No, no, no. But before you added the 280, the 250 changed its position. That's my point.
It
But my
didn't
point is,
actually.
if you insert things in a batch in the tree, it's gonna rebalance by itself. It's the structure of the
No, no,
tree.
I'm not. No, that I'm not questioning. I understand it's gonna rebalance itself. My question is,
Like
you
The
have
numbers, they will stay the same.
we,
What will change is this structure, but
yeah,
that
but
doesn't
then I have
matter.
a question. When you say persist the index, what are we writing to the disk?
Well, it's on all unordered in the disk, right? We're just writing to the end. That's it.
We are just writing to the end. But we're writing what?
Oh,
That's my
the
question.
row. Oh, you mean the, oh, right. You're talking about the index, right?
Yes, yes.
Oh, you're writing the sequence of commands you run of all the history. Like first add this index, then add this index, blah blah. Oh, I added a new row,
Oh, so
then add it to the end of the file.
when you load, you're basically gonna rerun the commands to rebuild the tree in
Yeah,
memory.
and that is not really expensive because well, it's just a I think it's just a when, right? To build the tree, to
Okay,
go
okay. Now
iterate
I
over
think I
everything
understand.
and just
Okay, now I
It's
think I
basically
understand.
a tiny interpreter for a tree building language.
Yeah, pretty much.
yeah.
Okay,
Well,
okay.
we already have that by the way on the file I found the C file for the B plus. It already has like an insert, right? So we just look at everything in like two values in a row. It's like a problem of those like exorcism or
Yeah,
something like that. That you just read like each row like and then you just it's like what's the name? Advent of code. Like
yeah.
literally that input. So anyway, that's not the best approach, but I think that's
Okay,
decent for what we
now
want to do.
after 30 minutes of Professor Magita's class, let's try to go to the code now.
Yeah,
So I'm gonna close this, and now
Professor.
let's try to read the build pages function. So this is the function that does the slicing, Marinho. I remember that much. I remember that much.
Okay.
And what is this thing doing? This is going throughout how all the pages that we're gonna have. So we know how the max amount of pages that we're gonna have, which is called page bound.
Okay.
We know the initial page number. So these are basically the indexes of the pages. That's what they are, right? Then we need to detect how many bytes you're gonna read to do the slicing, the current slicing, because this is a for loop. So the way
Okay.
that we decide that, we multiply how many entities per page we're gonna have with the size of one instance, right? And we check if this is greater than the remaining bytes that we have to read. How do you know how many bytes you have remaining? Easy. You pick the total and you subtract the amount that you already read.
I see.
Okay. This code is done in a mutable way, I should say. And this code in contracts is doing that in an immutable way. Uh, that was one of
How peculiar.
the tweaks that I did for migrating the code.
Very
Uh,
peculiar.
very peculiar, yes. So then, if this is true, if this thing is true, that means that we're just gonna read the remaining bytes. Otherwise, you're gonna read the amount that we expected. Okay. Then we're gonna update the amount already read. That means we're gonna update the variable because again mutation. Then we're gonna read stuff, right? So we're gonna put into this buffer this amount of bytes. I don't remember the API. Is this the beginning or is this the size, Magita?
So this is the chunk you read.
Yeah, so this is the amount
So
that you're
this
gonna
is,
read starting from this.
for example, I'm picking the page number. Oh, sorry. That's the index by which we'll start reading
Oh,
on
okay.
the
So
disk.
this is the position
The
that we're gonna
offset.
begin.
Yeah, the yeah.
So
Mhm.
this is where to start, and this is
Yeah,
the
this is the
amount to read.
chunk.
Yes.
Yeah.
This is mutation, so he needs to ignore. Makes sense. We are mutating the buffer, which is in here.
But that's
Then,
not that's not I don't ignore because it's mutation. It's because the API of the function returns a I think the amount of bytes read, which I think is pretty useless, so I just
oh,
ignore.
okay. So it's basically this. It's exactly how the C functions in for file descriptors work.
Yeah.
So when you read it, it throws it out how many bytes you read.
And I hate it because I had to build a buffer mutable because of that and fill with like you see the line 113.
Yes.
So yeah, I had to do that crazy thing.
Yeah, we are not doing that also. We are not doing that also. Then we are basically getting the instances. So you grab the buffer with the bytes that we know we're gonna read, because basically there are many instances that we've read, right? Because we read this amount. So potentially many instances were read. So then we grab the instances by doing chunk by size. And we also just pick because maybe is this possible that we have more than the page bound?
Uh, if
Mm,
you well, you can let me see. You are reading a chunk, right?
yes.
So I would say yes, because the point is the page number is not really the thing that is controlling the amount of bytes you read. It's just controlling the.
Oh,
Mm,
okay, I see. It is possible. If
uh,
you pass gigantic numbers here, I guess. No. If you pass gigantic numbers,
well,
this is not gonna
because
allow you.
yeah, I'm thinking here because if it's less, yeah,
Anyway,
if it's
that's
more than that, it will default to the all size. So I don't
yeah.
think so. Yeah, maybe I just did that.
Yeah, anyway, the thing that matters is we are grabbing the instances. So these are basically the entities. Not the entities, the rows, right? So each row of a specific table. I should be very pedantic. I should not say entities because the entities are logical entities. So these are instances. So basically rows. Then we are creating the indexes from the instances themselves. And how are we doing that? We are doing that by mapping. So map I basically gives you the thing and its position in the array.
I
And
see.
then we are deserializing from the byte stream. So this is a bunch of bytes. This is a bunch of bytes. We are deserializing based on the schema, and we need that, and we need to know the entity name because we need to know how to the heck to deserialize that.
Okay.
Uh, then we're gonna deserialize this, and this is a map. The return of this is a map. Why? Because a row, a set of rows. I don't remember why this is a map. I just remember that it is.
Wait, what is oh the attribute?
Yeah. No. The return
That's
of the
the
deserialization is a
info.
map.
That's the information for the uh the deserialize in my case it gives a map with the
No, in our case as well. Remember that
attribute.
I changed that?
I don't know, but it is an attribute pointing to the bytes, right?
Oh, we're not. I'm
To the
not printing that
deserialized thing.
anymore.
Sorry, it's the column. I think I call it columns. Can you search map columns, something like that?
Map
Yeah, it's a
columns
type. Just search for column.
like this.
There, column map. It's
Column
a
map.
string to a value. You see?
What is the key?
Oh, the name of the column.
Oh, okay. So the deserialized return is a column map.
Yes.
Okay. Okay, good. Uh, okay, so you're here. So then we're gonna try to find the attribute name. So because maybe you asked for age, for instance. In this particular case, Mageta is already assuming that the attribute index is gonna be related to an integer value. But this is just for simplification purposes. So then he's gonna try to do this. So the try find will give you like, oh, I found something, and the value in that map we using the attribute to index key, which is age in our case, for instance, and it's gonna return you a value. It's gonna return you a value, and then you're gonna put
Tuple.
that in a tuple
Yeah.
with the index, with its position basically. Because again, the
See.
I is the map is coming from the map I. He has like how crazy is that? Magetta has better error handling than our version. That's bad. That's bad because we
Yeah,
don't have
that's
any error handling. Any. We're just gonna explode, I think. And then so this is creating the indexes, and then he's basically returning the two things, right? And because and no, not the, because of that.
And just recall that this is reading just one chunk. So we need to read again the next chunk, right?
Yeah, but
So I
this is what the
return the
for loop is
amount
for.
already read. I know, no. This for loop is just for one chunk.
I don't
A
think
reading
so.
the amount, no, it's the amount of pages that fit to one chunk. That's why I return the amount already read. That's for the next thing, which is the build pagination.
Wait. Then I need some clarification. So this for loop is only building an arbitrary amount of pages to read a specific chunk.
Oh, wait, say it again.
As is a chunk composed out of pages, or a page is a chunk?
I'm saying the binary chunk. Like it's a portion of the disk you read, and then you have pages pointing to this. But you can only have this X amount of pages at once. So you read the thing in like 10 pages, you load the first chunk, then you offload the pages, you flush them, and then you move the offset to read the next chunk of the disk, and then you load 10 pages again. You see?
Oh, okay. So you pick a chunk, which is a bigger slice from the raw, full-blown data. Then you slice the chunk through into pages.
Yes.
Ah, okay. That's important nomenclature. I got that wrong for the first time. Nice. So this is to read a chunk. One chunk we made X amount of pages. Doesn't matter. And then we return how many the amount that we read and the pages for this chunk. Cool. Next, so the caller of this function is called build pagination,
Yeah.
which grabs the schema, the entity name, the relation to index. I always forget what the heck is that. This is the second time I'm trying to remember.
Relation to index is the relation is a entity. I think what you mean. It's which entity, which table you want to build the index on.
Is which table you want to give me an
It's a
example
table.
of
It's a table.
this.
This is basically just a string with the field metadata is just like holding the position of the field in the disk and all the other things for serialization. That's it.
We don't have that. We're gonna have to make that. Okay.
No, we man, like this. We have an analogous for this. I'm pretty sure.
Uh, like, give him an
Like
example. So this
this
is
is the
like
table.
the programmer table and
Like just look at where I use that. Can
okay.
you see?
Yes, you're using in here.
Yeah. And what do I do with that? Get the relation size to get the size of the instance of each instance, right?
Oh,
And
instance is a column. No,
instance is no, sir. Instance is
is
a
a row.
row.
Instance is a row.
Yes.
Yes, instance is a row. Okay, so this is basically.
Column is the what I call attribute.
Wait, why are you having this if you have the schema and the entity name? Couldn't you do a lookup?
I could, yes,
Ah, okay. Okay, that makes a lot more clear. So this is a table.
yes.
Okay. Then we have the
That
attribute to
it's a
index.
table you want to build the index upon. That's
Yes, yes. But you could retrieve that same table from the schema. That's my
yeah.
question.
Because here's the thing, I passed that first because I felt it was instead of like searching in the schema, it was better just to pass it over if I already have it, right?
Yes.
And I did. But I forgot to remove because I passed down the entity name for error handling. If you look on the other thing.
Ah, okay, I see. Okay, I see. Okay, you pass the attribute to index, so basically what column in this table I want to make my index based on. So H, for instance. The initial page number and the amount already read. So is this zero in the from when it starts?
Yes.
Okay. Then what we're gonna do? We're gonna discover a size of a row. We're gonna discover a size of a row. We're gonna discover how instances per page we're gonna have, because we know the size of the row. We know the total amount that we're gonna spend. This is the size of the chunk, I guess then, right? This is the size of a page. This is the size of a page. Sorry, it's instances per page. Then we create the file
Uh,
descriptor.
I have a question actually about the page size.
Sure.
Um,
Mm-hmm.
why is it not a power of two?
Uh, it could be. I just put like as I said, like for now, this is just an arbitrary size, and I'm picking in KB, right? Uh, like in a normal database, they have statistics about the like for example, depends on the use case, right? So for example, SQLite, I think it uses for mobile, right? So they cannot have a very big, like historically, they cannot have a very big page size because, well, it was based to embed things in like crappy phones, right?
Let's
Or
see.
embedded systems. So the page size is very low. It's like 4K
Yes.
bytes,
Yes.
which is a
Yes.
number they found was useful.
Yeah, but probably
SQL,
this is empirically
yeah, probably they
picked.
do calculations with like saying, okay, this probably like leaves on the average case to less fragmentation. I think Oracle they adapt the page size depending on the data you have to reduce. If I'm
Yes.
not mistaken, or it was DB2, I don't know.
Mhm. Mhm.
So that's a value you can tweak. I just like I didn't make any of these decisions, right? I just say, ah man, let's use 8 and that's it.
And by the way, Marinho, I want this to be in a struct. This value. We're gonna just retrieve from the struct. But this is like future improvements. Anyway. Then we open the file descriptor to read the file. We do. This is
You know
probably
what is the
some.
use in F sharp, by the way?
No, I don't know what's the use. I actually don't
It
know what's the use.
disposes it disposes the thing when it goes out of this
So
context
this is
by default.
defer.
I well, I think so in Rust, right?
I think I'm
Mm,
specifically saying using the Go langs defers in this sentence.
Okay, I don't
not
know either. So
not quite, because defer lets you call an arbitrary function at the end of the scope, and use, presumably, since it doesn't say explicitly which function it's gonna call,
It has
probably needs you
yeah.
to.
I mean, you can kind of think it is the same because the dispose is just a method you can overwrite, right? So
Oh, so you
could
can
be like,
overwrite that.
yeah, you can. It's a
Okay,
class.
so it's just an inconvenient defer then.
Yeah, it's inconvenient. Yes.
Okay, okay. I don't know what is this nonsense. What the heck is this?
I that's useless actually because here's the thing. I first used the read without the offset, right?
Mm-hmm.
And then I thought, oh man, I'm gonna have to seek the pointer for the file all the time. But then this is actually useless. I'm just pointing the offset, like this, the pointer of the file to the
Yes,
beginning.
to the beginning. Yeah, that's what I thought. And but isn't this already the case after this line?
No,
No.
no.
When you open a
Uh,
file descriptor in F sharp, it's not pointing to the
actually, no,
beginning.
no, no. Sorry. The first time, yes, it is. But
Oh.
if I read it again, because I remember that this is just one passage of the loop, right? We're gonna have to loop that. So I would have to change the offset by the amount of bytes read. You see,
Ah, okay, okay, okay.
amount already read the variable.
Yes, okay. Why are you not doing that?
Well, because I'm just reading once.
Oh, okay. Okay, so this is not useless. This is to remind us that we need to do
Yeah,
that.
yeah. This is yeah.
Okay,
This is
then
useless.
max page at once. So you are basically saying, at each given chunk, I'm only gonna read 64 pages.
If
Okay,
I cannot read it all, then too bad.
yes. Then we're gonna
And
call
why
the
did I
function.
choose 64? Because it would be 64 times 8 kilobytes. So I think that's a pretty good number already.
Okay, yeah, that's a pretty good number. Then we're gonna call the function that we just saw, and as we saw, this returns the amount already read and the pages. Then it comes the cool part, because this is a fold within a fold. A fold within a fold. How crazy.
Yes.
You're gonna fold the pages that you just got. You're gonna fold the pages. So a page is composed out of the instances and the indexes. Let's keep that in mind. So let's start with the outer fold. So this is basically this is the initial accumulator, right? Because we're creating a tree, and this is the container that we're gonna fold upon. So let's see. The first fold uh, picks the accumulator in an element. Makes sense. And what the heck we're gonna do about that? We're gonna pick the indexes of the element because we have instances and indexes, and the current state of the tree, and we're gonna pick that and we're gonna insert into the tree
Mhm.
using a key and an offset. This is because an index is a tuple of two things,
Yeah.
which is the value, and this is the I from the map I, which is we are calling here offset.
I'm calling offset. That's a bad name, right? It's not really an offset. It's an index in this very page you're currently at.
Yes, exactly.
There might be a bug there, by the way. I'll hunt that down.
Okay, and yes, okay. I'm actually a little bit surprised. Does this returns a new tree?
Yeah. No, no.
Wow,
Yes, this returns a new tree. Yes.
wow. I thought that it would mutate the crap out of
Yeah,
this.
it's funny because the C thing doesn't mutate, but the C sharp thing it does mutate. It's funny.
Okay, that's unexpected. Then
That's
after you have
backward.
the yeah, after you have the tree, we just create what we are calling in Racket the pager, which is a set of pages, the tree for doing the lookups, and the amount already read. And then we are using such function build pagination in this function, and this is the real deal because this is the function that is going to be responsible for doing projections, right? AKA SQL selects. Um, So what we need to do, what we need to have on hands in order to do a search? We need the schema, makes sense. We need the entity name, makes sense. We need the project param, which is an expression project parameter.
So
So this is the
yeah,
predicate.
so this is no, this is the like select star. It's the star.
It's the star.
Like when you type the columns you want from a table, right? That you're
Yes.
projecting. Like that's basically the either the list of parameters you want or the star.
Ah, okay, okay. So future proofing, future proofing.
So I'm calling right now and just calling all and restrict, which gives you a list of attributes
Yeah,
that aren't cheating, by the way. But
yeah.
that's it.
Then you have the name of the key that you want to search for. So this is would be in the actually, I'm confused. Why do you need both? Because this can be restricted to only a single name.
This is the select blah blah blah, and the other is the where.
How is this aware? So you're searching for
Oh,
age equals to 1, for instance?
I want pairs like so I'm cheating because that should be a predicate, right?
Yes.
So I'm assuming equality. That's no because I just did this on because I didn't have the polymorphism, so I just
Oh.
assumed the integer age, whatever, right?
Oh, okay. So age integer. That's why we have a string and an integer. That makes
Yes,
sense.
but it should be in that case, it should be like any arbitrary thing that you can compare, right? That implements the equality in your query language.
Yes. Okay. So now I have a
Not
question.
equality, but the operator you want. Right? You should receive the operator and the list of values you want to compare, and it could be a list of those, right? It could be, for example, uh, A equals true and B equals ABC. You see, like
Oh,
a
okay.
string.
No, no,
So on
yes,
that
yes, I
B
understand that, but
integer,
I was just looking why we need the schema to the lowest level. We need because we need to deserialize it. That's why.
yeah, which is what I want
Yeah,
eliminated,
because
by the way.
because you were doing in here.
Because right now it's pretty dumb because we build a tree every time you do a search. Like, it's
Yes,
crazy.
yes.
And you
Uh,
serialize everything. So
yes. So
yeah,
then he tries to find the table in the schema. If he doesn't find, he throws an error. Makes sense. If he finds the table, the AKA relation, he's gonna pick things about it. He's gonna start some stuff to initialize the pagination. So the initial page number and the amount already read, which both starts at 0. Then he's gonna build the pagination, creating the last read chunk. So this is the amount that we. Oh no, this is actually the pagination record, the last chunk. So he's printing the pages, which are the leaves. Printing the leaves in the screen. Mutating the amount already read with the amount already read from the last read chunk.
Mhm.
Then he's doing a pattern matching. He's doing pattern matching on the projection param. I don't know where the heck this is coming from. Oh, from here.
It's an attribute. Yeah. It's
Yeah, so
a
it comes from
parameter.
here. So if it is all, he's going to return none because this
Yeah.
function
Right
is
now,
mocked to assume
to
this.
just one. Yeah.
Then, if it is restrict and attributes, he's gonna. Okay, there is he's missing a check. You should check if this key name is within the attributes.
Yes, but I'm
Because
just
maybe
like
in the where clause I'm trolling.
no, it is right. It's actually lacking because here's the problem. Like I use these attributes. Oh no! Wait, this is wrong, Lemons. You're looking at the where, right?
Yes.
That is not the where. That is the select. So those are
Yes,
the
but
members you
if
want
I do a
to look
select,
at.
no, but if I
This
do a
that's not
select with name and age, and in the where clause we have banana, how that's gonna work?
sorry. The where doesn't
Yes.
matter. That it will be there, right? Well,
If you have banana in the table, that makes sense. That
supposedly.
makes sense. That makes
But
sense.
the attributes is not really part of anything on the search. It's just the thing, the columns you want
Retrieve
to
from.
restrict.
Yeah. Yeah. Okay. Yeah. My bad.
So
My bad.
like you have like apples, bananas, and watermelons. I love watermelons, by the way. Uh, and then like you're searching by seeds inside the watermelons, which is another column, right?
Yeah.
Uh, then like yeah, that doesn't matter because the attributes you want they are going to be just the three fruits, right? They're not going to be the seeds in that case.
Yeah.
That was a crazy example now that I think
Yeah.
about it, but
Yeah.
anyway.
That's fine. Then he's gonna use the tree dot find and get value from the FFI, passing the tree, the key, and this. Uh, yes, and then if it's -1, that means that we
Ah,
got none.
kill
What?
me, kill me with this.
And if you got the offset, which again I don't think this is maybe the best name. That means that you can, and then
Yeah,
Magetta
this
is
is
just grabbing the first page, uh,
no.
the
And
first
grab.
page,
So yeah, that's what I'm cheating as. That's correct.
and he's because this is basically an index to you to get from the instances
Mm-hmm.
that you saved in there, and then he's deserializing that again, mapping. Oh, here's the contains. Okay, so you were not cheating.
Mm-hmm. No, I'm cheating on the pages. That's what I meant. Yeah.
Yes, because he should be
So,
doing through the search throughout all the pages. That makes sense.
mm-hmm.
Um okay, I'm actually a little bit. So what the heck are we deserializing when you do that?
Well, at that point, for I've Queen, like what you have in the page is the binary for the row, right?
No, that's why it's stupid. Okay,
Mm-hmm.
because you already did that before. Okay.
Yeah, so we could either like converge both, but I don't think that's necessary. Because well, first reason, like we should already have built. Oh, sorry, my tongue is numb. No, uh, we should have already built the index up to that point, right? We should have just been
Yes,
reading
yes. And then what
it.
the heck is the map filtering? Oh, it's filtering the attributes that you are interested in.
Yes, the ones that you
Yeah,
want, just the only the ones you want selected.
yeah. And I don't think Magita added that here. Yeah, we don't have the type signature of the result, but probably this is returning like a list, a maybe.
And if you are interested into seeing how I'm running, there's the executor project. You can go there.
Source program
Program. Go all the way down, I think.
search.
So I just receive that thing from like
Oh, it returns a map actually.
yeah.
Map to array.
And
I
then I
see.
send over the socket. Yeah, man.
This is
That's
so
it.
baguette, man. This is so baguette. Oh, I loved it. I loved
Okay,
it.
let's do it, man. So last time we ran, can you run again the project on Racket?
Yes. So the last time we managed to. Uh,
Wow, so meaningful looking at this.
yeah, no, that's the thing. These are just bytes randomly, right? So it's crap.
Hmm.
And these are the actual indexes. This is actually what really matters. I actually don't remember why we have a 21 and a 123. So
We had a bug, Marinho, because Lemos was typing the type like bytes with the question mark, right?
yeah. Oh
Right.
yeah.
He was typing bytes
Yeah, it
instead of
was there was
byte.
an S here, man, and that took a while to discover. That took a while to discover. Holy fuck. Um, yeah, not proud of that at all. Not proud of that. Anyway,
That actually should have been a list of bytes in the plural instead of a list of bytes singular.
yeah, I think that we can replace this with this. We can
Because
even we can
the
even
difference
check now.
is bytes plural
Oh
question
no,
mark.
actually no.
No, Marinho
Because
meant
bytes,
just bytes, right? Oh,
Oh.
but
I
oh. No, we're gonna have to combine. My tongue. I think what he meant is that it's still a quoted list in the end. We have
no,
to
what I
change
mean
that.
is that
Oh no, that's
bytes.
wrong actually. I'm gonna have to change the implementation to change the contract.
No, what? Let me just finish my thought. Bytes in the plural checks if the value you are passed is a byte string, like a literal sequence of contiguous bytes.
Yes.
If if you do list of bytes, what you're actually checking is if the value is a linked list where each element is an integer between
Mhm.
0 and 255.
Okay, that explains a lot.
So you have to change the structure, right, to make that
No, no, no,
compatible.
not only
Yeah,
the
instead of
structure. I'm gonna have to change this code, and I'm not really in the mood of changing this right now.
Yeah, just leave it like that. That's fine.
No, no, no. We're gonna enhance this at some point with
For
like
now, man. Like we
to
don't.
do.
For now, I don't want to do that.
No, no, no. We're not gonna do that today. What we're gonna do today, starting from the build pagination. Uh, Let me go back to our previous code here. Yes. So yeah. So this is what we're gonna do today. This thing. I think, Marinho, correct me if I'm wrong. After this class of Mageta's professor, I'm very, very like comfortable now reading all of this. It makes total
I
sense to
feel
me.
sorry for you, man.
No, no, no. I'm not being ironic because last time I had like an idea of what we were doing, but I was really
Which makes
focused.
it even worse. I'm sorry for you, man.
No, last time, like it was not your fault. It was just that I was very tired last time. I'm still tired today, but better than the last session for sure. Uh, but I just focus on okay. Let me try to understand by reading the code. And 1 week
Mhm.
passed, and I already forgot everything, and now I just know everything again. That's how actually that's what the book that I told you guys that I'm reading talks about. This is this kind
Oh
of
man, like scroll up a
reinforcement.
little bit.
Go.
Scroll up just a little bit to the FFI in F sharp.
Oh yeah.
Uh, Scroll up there. So man, can you tell how hard it is to do this in Okamo?
Oh wait, is it hard? I have no
Man,
idea.
it is impossible.
It
Like
is
it's borderline
impossible.
impossible.
Really?
Yes, just search. You have to
FFI
modify the
can.
C source code to import the Okamo interface. Like it's horrible, man.
Are you really sure
Search
of
for an
that?
example. Like
Example.
yeah, you see that those,
Implementing primitives. So you have this crap, whatever it means.
and
What
then
is?
in the
Oh,
end,
there is a
like
camel prim.
dude, I was pissed because in the end you handle the same way. like everything, like in native integers and such. Like you can have some certain degree of type safety, but not that much. So yeah, you see those? You have to import those in C and then call the OCaml thing to
Oh, that's
compile.
very
Like
inconvenient.
that's terrible, man. If you
That's
have
very
like a
convenient.
if you have a big library, you're gonna have to convert the C code to adapt it to make the bindings for OCaml. Like it's horrible.
Oh, okay. So the Camel FFI assumes that you are not gonna be pissed
I mean,
to change the C
there
code.
might be a way.
Yeah,
Maybe
we
I
are.
just
Maybe
don't
it's a
know.
skill issue, and we're just dumb.
Yeah,
It's
it could be
possible.
a skill issue, certainly. But it's way more inconvenient than F sharp. Like
Okay, okay. That's good to know. That's good to know. Okay, okay. Let's
I'm pretty
let's.
sure that some OCaml fanboy was
Yeah,
like
yeah, yeah. And
screaming
I
about
know I know them. That's the thing.
yeah.
That's why I don't want to say that it's just okay, it's terrible, it's trash. Let's discard it. No,
Yeah.
no, no, no.
We
We're
ain't
not
even care
saying that.
more. But anyway.
Yeah, we're not saying that. Something that I had in the back of my mind that I got because of diffuse mode is that there is a thing. Oh, there is this. There is a thing that we can optimize in here. Uh, let's pick that, throw it in here. Yes, let's remove that and let's remove this. Let's see if this works. Yes, it works. Thank you, diffuse mode.
If it stopped working, that would be funny.
That would be hilarious. Yes. But it's better now. Okay. Now let's go. So define. We're gonna have a function called build pagination. And what this thing needs? This thing needs the schema. Right now, Marinho, we're not gonna care about optimizing it. So if
While you
we
do that, I'll be right back.
if we understand later that we could like get rid of some parameters and stuff like that, especially if it's these many, we're probably gonna put that in a struct of some sort. Although to do that, we would have to make a generic interface, and I don't really know why we would do that in this particular case. I just miss Rust's structs when this happens, and I don't need the interface. But okay.
Yeah, if this was closure, I would have said just use a map.
Then we're gonna have the attribute to index.
But unfortunately, this is not closure, which means we don't have convenience map manipulation. I mean,
And
it's good, but it's not
source.
convenient the way it is in closure. So using a map is kind of like, it's mildly annoying.
Yeah. Uh, and the amount already read. And that's it.
Um,
So let's just start with this party. So the first thing that we're gonna do is to make a let. I think that's exactly what we're gonna do first here as well. So uh, let. Uh, so the first thing that we want is an instance size. And for now, we actually need. Oh fuck! What is a relation index again? This is the. Oh, this is the table. This is the table. This is the table. That's very interesting. So, do we have a thing about that in our AST? I don't think so. So maybe you're gonna have to make
can't
that.
yeah, can't we compute the instance size from the schema?
Um, can't we compute from the schema? No, it's not about we can't. I'm 100%. I guarantee you that we can. I just want to know how hard it is.
It's
Um,
just grab each field, get their sizes, add them up.
yeah, so I have no particular. Wait, so is this a struct thing? Can I ask for the size of a field in a struct? Can I do that?
No, by size,
Ah,
I mean their size in bytes, like when we serialize it.
when we serialize it. I don't know what you mean. I really don't know what you mean. For me, this is asking what is the size of a row in this particular table. So this is just pure logic, my understanding.
Yes, it is. It is.
This is just pure logic. We
But the
have a
size of a
problem.
row,
We have a problem.
why?
How the heck are we gonna know the size of a table if we have arbitrarily wrong constraints? How are you gonna know the size of
No,
a row?
no, like a row, the size of a row is just the sum of the sizes of each field,
Yes.
and the sizes of the fields are statically known because we need that for serialization, right?
Uh, they are not statically
And-
known. Some of
Oh,
them are, but not all of them.
Wait, what do you
but the
mean?
ones that
Like even a string, I'm pretty sure that when you
No, no,
instantiate the
no, no.
string,
A
you have
string
to
and a
know.
number, those are instances that we know statically the size. But we have a dynamic thing, which is the constraints. It's an arbitrarily sized Racket code.
No, but
but the
no,
constraints
but
are
man,
not
like that's just
something.
concerned with the columns. That's not concerned with like anything else.
Oh yeah, I need to remember that. Constraints are not columns. Constraints are not
Yeah.
columns. So that's thank you.
Like you are concerned with the type size in there, which is
Yes,
static. Right?
yes, which is static. So we're gonna have to make that function. We're gonna have to make that function. Now, are we gonna do that on the level of the schema as uh, as Magetta did, or are we gonna just do the lookup of the, because again, this table is exactly this table that we could look up from the schema. Okay. What we could do is to make a function on the schema level that picks a name of something and returns its size instead of passing the relation to index. We could do that way. What do you guys think about that?
Um,
Uh,
Because
I
this
mean, the
relation
relation to
is this, right?
but like the relation to index, uh, we should be able to reach the schema from there one way or another, right? Because the relation to index is the table that we're actually interested in, right?
Yeah, no, but the table that we are, this is the like this is the materialization of the table. What I'm saying is that we could get the same thing by just doing a lookup in the schema using this name.
We
But
probably could, yeah.
I'm proposing us to remove this as an argument and make a function on the schema for the schema that picks the schema, picks a name, and returns me the instance size of that name if it is within the schema. That's what I'm proposing, basically. Did you get it,
I don't
Marin?
see. I think I get it, but I also think you are slightly confused.
What am I confused about?
Like we're getting this schema as an argument already anyways, right?
Yeah.
Why would we need to do a lookup with the entity name? We already have the schema at hand.
No, I think you are
mm,
confused. We need to do the lookup if you don't have the relation to index. Let me try to explain more. What we are doing here, we are grabbing a table, right, which is a map between columns and metadata. Well, so this is a table, a
Okay.
logic definition of a table. And this is the table name that we are also conveniently we have that at hand. We have a schema, which is a map of names to this, right? So what we could do, we could remove
Oh,
the
right,
relation to
because
index, do a
right,
lookup
because
of
the
this name on
schema,
here, and we will get the same thing. But I'm proposing to go
right,
further,
right,
make
right.
a function that picks a schema and an entity name and returns the size already. We don't have to have this intermediary thingy going on. We can just get rid of that. Because as far as I can tell, the relation to index is only... Oh no! The relation to index is also being used to call the build pages.
Well, I pass it down for error handling, but I don't really use it.
Is that
Or is that no?
for
Just give me a
sure?
sec.
So the relation to index, where the heck are we doing oh, okay, we are using for the error messages. That stuff.
Yeah, to get to which field, right? I was just like preparing to do to remove the v integer and handle like different fields.
Yeah.
But I didn't finish that.
You see, Magetta, Lemos was actually a step ahead of you when he chose to not implement error handling, because now we can eliminate this parameter.
That was my intention all along.
Man, levels is foreseeing already.
Okay, so my proposal is the following. So let's get rid of this and just do the lookup in here, using the entity
Yeah.
name in the schema.
Yeah, I forgot for a moment that the schema is actually the description of the entire database instead of just
Yes,
one
yes, this
table.
is
Yeah.
the source of
Hmm.
truth of things that we're going to classify as facts, basically. So this is the entirety of it. So I actually have no resemblance on how the heck we do that. So let me go to IO. So is there like a write table? Yes. So how in the heck do we do that? Um, that's not really what I want. I want something like a rash half. Oh, so this is how you do it. So this is how you do it. So let me copy paste. Um, oops, I definitely didn't want that. So let's grab this cond and let's throw it in here. So we don't have a table name, we have an entity name this time around. So if we found it, we're gonna do things about it. And if we had something else, what is the else in the cond? Cond racket.
It's literally just else.
But is that like the double column? Double column something something?
No, it's
No,
literally just
there's no
else.
double column, right? It's
Symbol.
just
The
column.
symbol else.
Else like this?
Yes, it is a keyword recognized by the cond macro.
Okay, so this is gonna be for now just a print, and I'm gonna say did not find uh, the entity name. Okay.
Mind you, it's a redundant keyword because you could have just written true and that would have worked, but
Hmm. At least it's easier to read, right?
I agree with Mageta. So now what the heck are we gonna do here? So let's get rid of the previous code, and this is what we have. This is what we have. So in here we're gonna have another let actually.
I just find weird the choice of the word else or a conditional because it's basically like a switch case, right? Not read. It's like you're checking each condition individually, right?
yes.
Like it should, for me, it should be like otherwise, something like this.
Yeah, that makes sense to me as well. Okay, so the first thing that we're gonna make is actually the instance size. So we're gonna have to make a function later, which is entity size, which picks an entity and returns the instance size. That's cool. Uh, so then we're gonna have the instances per page. That uses the instance size. So, oh, this is why it's wrong. I forgot a parenthesis. What a sin. I forgot a parenthesis. Yeah, now it's correct. Then we're gonna go here, actually here, and we're gonna, oh, I was about to put a star here, that's why. Then we're gonna make the instances per page, which as in Mageta's case is gonna be hard coded as 8,000 divided by the instance size. What else do we need? We need the file descriptor, which we are not using it. So I forgot, how did I change this? Because I think I'm doing the file descriptor here. Yeah, so there is something called file name. Where is file name in here? It's from the entity name. So we don't need the reader at all. So these two lines are gone. Although this line here, we're gonna have to do something about that at some point because I'm not creating the file descriptor in the build paginations. I'm only creating that in the build pages, as you guys can see here. So this is where I am instantiating the file. but maybe I can just jump to it using the amount already read. I can just jump it. Yeah, I can do that.
Uh,
Okay.
yeah, I'm pretty sure. I'm pretty sure there are options in the. There are ways to do that. I'm pretty sure.
And then we're gonna pick the max pages at once, and I'm gonna put 64. Then we're gonna call the build pages. The build pages is a little bit special because it returns values, if I remember correctly. Yes, it returns values, which means that can we do a define values within a let? I don't remember, Marinho.
We can actually.
Okay, so define values, and we're gonna call build pages, passing a shit ton of arguments. So the first thing that we need to pass is the initial number, which the initial number comes from the build pagination arguments.
You may think as a frivolous thing. I say it's the Silk Road pattern
What is the
in
Silk
action.
Road pattern?
You pass as much data as you can down to other functions, and then you just keep passing to other functions.
Yeah, so instances per page, this is coming from the lat. Max pages at once. Um, then we have the file descriptor, which we don't care. Page bound, instance size. So now what is the thing? Okay, instance size, amount already read, and the ton sheet of stuff. Again, I just miss Rust structs. I just miss them. Instance size, amount already read. Then the attribute to index. Where is the? Oh, it's coming from the other thing up there. Okay. Then we have the schema. Then we have the entity name, and then we have the entity itself. That's it. So you're gonna pass all of this all of this to get the pages and the new amount already read. So that's what we have. That's what we have. So after that, what the heck are we gonna do? We're gonna do the double fold. So the double fold definitely is not gonna live in here. It's definitely gonna be a separate function. Uh, so let's go here. So define create b plus tree. And what the heck we need to do in order to do that? So we need the pages. That's it. We just need the pages. Okay. So let's put in here pages. What is the best way of doing that? Threading. There.
That's an option. Yeah.
Pages. So we're gonna do a fold.
By the way, we
Uh,
have that on Emacs too.
yes, we have that in Emacs too. Yes.
It just has the
Actually,
thread first and thread last.
So
But those are the
I
only
did the
two. You don't have like
foldel.
anything else.
Okay, so no, it's not what I
yeah.
want.
Actually, the threading macro is not quite what you want because what you're actually doing is the function argument you are passing to fold will do a fold itself.
Oh yeah, that's true. Actually, we'll do a fold itself. So actually we well, let's try to do it in the dumb way first, and then we make it with the threading. So it's gonna be a foldel, and then here we're gonna have a lambda. Then we have the initial accumulator. The initial accumulator in here is gonna be the new pointer, and then and then we have the pages. So something and then pages. Let's
And that
go
something is
to b
that something is
plus
actually the boolean false.
false. Yes. So this is false. Yeah. Then in here we're gonna have a lambda. Such lambda will do the first one will grab the tree and the element, so the accumulator and the element. Fold L is the opposite. So this is the element and this is the tree. Then we're gonna do another fold on top of that. So fold L again. Oops. Fold
Lol.
L. Another lambda. The initial accumulator is gonna be the tree, and the element will actually be the indexes, right? So this is going to be page indexes element, I believe. So what is the thing? I already forgot. What are we returning from the build pages? We are returning pages. So what the heck is pages? Oh, page. Yeah, so we have, so this is a page, right? This is a page. This is a page. And we want the page indexes out of the page. Makes total sense. Cool. Then now we're gonna do the
It
second
doesn't,
lambda.
man. You know it doesn't. It's just a fruit of your imagination.
uh, which
Ah,
is this is another fold L. So the first thing is the element, which Margita is doing pattern matching here. For now, we're just gonna put element, and then the other one is gonna be the tree again. But then we have
that,
shadowing going on.
that
Uh,
append makes me so sad.
Well,
yeah, again, we're gonna
anyway,
make it pretty later. That's fine.
It's
Uh,
not a question of being pretty at this point. It's just you're taking an algorithm that should be linear and making it quadratic for no reason.
yes.
this was just what I had in my mind when I did it, man. Again, we're gonna make it pretty later, and we need to make these vectors back again because now we have lists, which is bad. We're gonna make those vectors again. So then you're gonna do an insert. I already forgot what is this.
I read an article that I I can say I think I disagree a lot substantially with it, but the point was like in the case of the F sharp, right? As far as I know, since it's a fold that it knows that it can be linear, it would just flatten it, right? The compiler, I mean.
Yeah.
Um, and the article was basically talking about like stop worrying about code optimization and rely on the compiler. And then like it went through a few
No.
examples that like yeah, you can rely on the compiler to make it like better code than like you would try to optimize. But man, like that's such a bad maxim to go by. Like first of all, you are assuming the compiler will have a specific behavior for whatever you're doing, right? Uh the amount of things you can do to go wrong, it's actually greater than the amount of things you do that like get right that thing. So in that case, it's just by mistake that uh, well, it's just a coincidence that the compiler can optimize that thing. But uh, if you can do this sort of like if it was a little bit, for example, if I wrote that mutably, I don't think it would because the F sharp compiler doesn't get mutability very well. So it's actually less efficient to treat things mutable. So people are like assume the behavior skewed
Pages,
way.
tree, amount read.
Yeah, you're basically assuming that the compiler is sufficiently smart, which
Yes.
strikes me as a very bad assumption.
But
There's
sometimes
actually a
Yeah,
they,
deeper
most of the
sometimes
point.
time
they
it
are.
is.
But
It's
sometimes
not.
they are. That's just to point
Yeah,
that
yeah.
out. Sometimes
Sometimes
No,
they
they
are,
are.
but the problem is
Pages,
sometimes. Like
tree.
it's not always.
Yeah, I agree.
yeah,
Oh man, this code makes me depressed. Looking at this.
and the other problem, one that's
Pages,
actually a little deeper, I think, is that this is something that Chuck
create
Moore wrote. I don't remember where I read it in his work, but it's something he mentioned
pages,
that um, the easiest place to optimize your algorithm is actually at
amount
design
read,
time.
Mm-hmm.
And the
amount
compiler has no say about the design of of your code. So
Yep,
like,
already read, and
that
this
makes
is the
sense.
new. This is the new. There, there, there. And what is the other thing that I think I added myself? Is the instances per page. Okay, right now, because I am not trying to optimize what the heck Magetta made, I'm
By the
just
way,
gonna go through
why are
them.
we not writing a database in Lisp again? Can you tell me?
Uh, uh,
You mean common Lisp?
no, he said
No,
eLisp.
eLisp, like
eLisp.
literally
Oh,
Emacs Lisp.
Emacs Lisp. Okay.
Yeah.
Man.
Okay, question.
And
Does
then,
it work? Because we are done. This is the end.
wait, let me see. I didn't pay attention. So build pagination. You define create b plus 3, which is the FFI function, right?
Yeah.
Uh, wait, oh no, sorry, you're just iterating. Never mind, you're defining it.
Yeah, no, this is not iterating. This is defining
Wait,
because I'm gonna use it later.
right, insert, entity, hashes, instance size. Then you
This
create
is
the serial
terrible. We
number.
should do something about this Marine later.
Yeah,
Ah, so bad. Maybe makes a little bit better.
no, it doesn't.
No, it does. And
I
what matters is
mean,
that we are building the pager after, which is this.
Well,
I
I would
mean,
say try to run, but it will just produce the tuple, right? The struct in the end. So I would say just try to do the no.
No,
You have
we
to
can,
modify
but
the
but we
language
can test.
first.
We can test what you said. So we can go
you
to
can you
main.
can you can print the struct. That's a thing that you can do.
Yeah,
Yeah, but
structs they
yeah,
have
okay.
good printing. So we're gonna remove this.
I would say that's not really meaningful, but at least it's one less thing out of the way.
Then we're gonna do this. So then we're gonna call build pagination. Build pagination. So as you can see, these are magic values.
Yes.
As you can see, these are magic values. So we have schema, then we need the entity name, which is
Oh, they
fine.
they are interpretable magic values, right? Let's
Yeah.
put it that way.
So then we have the relation index, which are not we are not really doing anything with it. So this is gonna
The
be
7 and 10
new.
and 4 are because the size of the fields, by the way. Just
Is gonna be this because you're not using relation to index at all. We're just passing it. Are we
You should
passing that
pass
further?
false instead of new.
I don't think we are passing relation index further. So for now, I'm just gonna comment it out. Then we're gonna have
By
the
the
attribute
way,
to
in
index, which is age.
Lemos, in a scheme dialect, if you have no value to pass, you should pass false instead of no.
Yeah, just my bad memory, man. Bad memory. I think it's because of common Lisp actually. It's because of letters. Uh, Next is an initial page number.
oh man, Belani told to my new boss, right? We were introducing ourselves, and then Belani presented himself as a Lisper, right? And then the guy started laughing like, "Ha ha, that shows your age." And I was like, and then, oh man, it's
Sometime,
fun.
if he ends up being your friend, you tell him. So about what you said the other day.
Yes, and then like after that, he saw me using Emacs, so oh man, I like the guy, pretty funny.
Is this not where we're? Oh, we're not doing that in this from here. We are actually grabbing. We need to grab Racket Tower DB B plus 3, I think. Insert unbound. Am I going crazy? Where is my thing? It's here.
Well, the thing is yes, but is that
B
for that
plus
reason?
3. Oh, I need to provide. I need to provide. That makes sort of sense. So let's actually put insert in here. And we already know that we're gonna have. But let's wait a little bit. Let's see if this works first.
And I discovered what was preventing me from using the LSP in Emacs for F sharp. My
Oh, okay.
day, I spent 4 hours trying to debug that, but
So
otherwise my
entity
joys would
size.
just run
Oh,
out.
okay. We need to make this function. Okay, that's
Right.
important. So we need to make the function. So how the heck we're gonna do that? So because this is a table, I'm actually inclined to call this table size, but now this can't be because it's gonna
Uh,
understand this is a field.
no, it has to be row size or something because this is not the size of the table. This is the size of a row of the table.
That's true. That's true. That's true.
Actually, you
Um,
should call it table dash row dash size
Uh,
because
well, it should be the size of the table, right? Independent if because there are two different things.
oh, this is a logic table. So this should be table size.
Here's the thing. Even like okay, think of this. You have a row, right? That has three fields, like an integer 32, another that is like a varchar, like 2, and they tell me another field, like a bool, which is two bytes, right? Sorry, just 1 byte. 1 beat, actually. Yeah, whatever. Like, yeah, you guys got the idea. Like, just think of three fields. The one that is variable is the
Is
string,
4?
right? So
Yes.
the point is, it should be congruent on my design, at least. It doesn't need to be, but on my design, it is congruent between the instance size and the size of the table. So
Yeah.
both are exchangeable.
Yeah, no, but in our case, that's what I said before. In our case, a table is a we're talking about the logic table. So when you calculate the table, the size of the table, you're not calculating. This is not the table that holds data, Marinho. This is not the table that holds data. This is the table that is in the schema, and the schema holds what? Logical definitions. Logical definitions. And a single logic definition of a table is basically the modeling of with constraints of a single row. Because a single row, all rows from that table must follow those constraints. So that's an important distinction to make. There is the table which is what holds actual data like rows, but this is not that table. This is the table that is the logical definition of a table, which is this.
this is the platonic idea of the table.
Could it be? Could it be? So
Don't call
uh,
it get table size. It's not. First of all, you're not getting the table size. You are computing it, and second of all, you just wrote a function call for that function with a different name, right?
yes, yeah, but that's
We
easy to
called it
fix.
table row size.
Yeah.
So
Okay. Do you guys think it's better name? Because for me, it's a domain incongruence to say that this is a table row size. Because this has nothing to do with rows at all. This is just the table which holds the definition of all the rows. All the rows must follow this definition.
uh, actually, uh, the thing is, the table prefix is actually a scheme convention where you prefix the name of the type that you expect to get as an argument in the name of your function. And then the function itself, it computes the size of a row, right? Given a table descriptor.
Okay. Okay, let's keep it like that. So fields, then we're gonna do table fields table. We're gonna do that. Then we're gonna have a problem because we don't know the sizes of the fields, right?
Why?
So we don't because that we just don't. So how are we
What?
gonna do that? We're gonna actually do a fold L, in which we're gonna extract the size of a single field in here, and we're gonna start from 0, and we're gonna do that throughout all the fields. So then, for each individual field, how are we going to calculate its size? That's a good question. That's a very good question. So this guy does not hold that information at all. It does not hold that information at all. I don't remember. Do structs in Racket allow us to put functionality when doing a constructor? Like when I'm creating a
I'm doing a
field. Yeah, when I'm creating a field like this, like field, position, and type, I'm creating a constructor, a field, right? This is creating a field.
right,
Could I
right.
add some functionality to this? Something like, I don't know, maybe constructor. that would allow me to when I receive those things, I do something else. You know what I mean? Because I would like to do
The
something.
close.
I would like to do something like this. So I put size in here, but you don't have to pass those to me. I calculate that myself.
You would have to create another function that does that, that takes two arguments and returns the third. But you actually don't need to do that. You can, like, you know how the serializable interface, it needs to know the size, right? Although it gets that as an argument for some reason because we could
No,
not
I
foresee the
know.
future.
No, yeah, I know why. I know why it receives the size. It's because uh, I think it's the size of the type. I don't recall actually. I don't recall. Yeah, I don't think I remember. But anyway, let's go the Greg way first. That's fine. So field size, and you're gonna receive a field, which is kind of sad because this is basically gonna do a let. We are gonna grab the type out of that. So field type field, field like that. And the answer to this let is basically doing type. I think it's size from type. I think. So let's go to type. Yeah, byte size. So it's byte size. So byte size. Because a field in this particular case is the size of the field doesn't matter its position, right? It doesn't matter its position at all. So it's going to be that. So then we can go back to table row. Yes. So in here, uh, it would be very nice. Oh, I'm
By
missing
the
the
way,
accumulator. I'm missing the accumulator. That makes sense. Uh,
fields is actually a hash table, so we have to do. I think it's hash values,
I think
if I
it's hash
remember
values as well. I
correctly.
think it's hash values as well. Hash values, yes. And then you're gonna put field size field. Right. So this is it. So this is the function. So this is the function. Now we can go back to pagination. And in here we can put row. Oh, I need to provide that shit, right? Yeah, I need to provide that shit. So provide.
I like the use of terms here.
It's very Magenta, right?
Not even I
Uh,
say this kind of stuff.
what?
Not even I am saying this kind of stuff recently.
Really? So
Yeah.
I should roll back to a better role model. Fields, field size. We are using this somewhere. Where are you using field size? I just created this
Field.
function.
Why
What
did
the
you call
fuck?
it fields plural?
Why did I call it fields plural? That makes total sense. It should not be fields plural. It should be field. No, it should be field size. Should be field size. No, this is doing something
All right.
completely different. This is doing something completely different, right? Yeah, this
Oh,
is
you
doing
have
something.
field size. You have the field size function that takes a single field and
Ah. Okay, so I want to do field size. Okay, but we are not. We don't need to export that actually. So let's go. Next error. Build pagination from main. Okay. So we are not doing something.
they're
We are
not providing it
we are not
probably.
providing it. Yeah. So let's go to provide. So how does this work again? I always forget. So I just put here.
Yeah.
There. Okay. Make struct type. Guard procedure does not accept correct number of arguments. So util 47. I have no idea how. So 47. checked guard. Okay, so this means that the pager is wrong. Pagination. So the pager has three things. Oh, I forgot to remove these things from here. Okay. Cool. Field type contract violation in AST 130. So AST 130. So what is the problem?
You expected a field, but you were given the number 0. Because
Mm,
I think the problem is the parameters are backwards in the anonymous function.
the parentheses are backwards.
Parameters like act and field should be field and act instead.
Oh, that's correct. That's correct. We first do have the element. Okay, build pages, arity mismatch. So to check that, you're gonna have pagination here and here. So I'm gonna go to build pages.
Ah, right. You deleted a parameter that wasn't being used. Did you change the call site?
1 second. Build pages. Yes. So here we go. So we have 3, 6, 7, 8. 3, 6, 9. So something is wrong. Something is wrong. I think I know.
Entity. You're passing the entity.
I'm passing the entity. Oh, this is gonna fail now because of the main. It's on the main. So build pages. Yeah. Okay. So there is a take somewhere, line 33. Expect a list with at least 64 elements. Oh, I think this is because of the take. So
60. Oh,
apparently,
right.
apparently Racket's take is not very, how can I say?
User friendly.
It's not user friendly, but it's very pedantic. If you want 64, it's gonna be 64, my friend, and you're done. How are we
But
gonna change that?
all right. So if you don't have enough, it will fail, right?
Yes, exactly.
I
Which is not
see.
the same behavior in Haskell, for instance, and apparently not in F sharp as well.
Yeah.
Okay, so how to fix? Do we have another take which behaves a little bit different? So lists, Racket. I really don't think we have. So take F, take the L. Returns a fresh list whose elements are taken successfully from list as long as they satisfy pred. The return list includes up to, but not including the first element of the list from which preds returns
That
false.
that's not really what you want.
That's not
Yeah.
really what I want at all. Yeah, I
You know
want
what I the
this.
like I really like Lisp, but you know what's the thing that I dislike?
What?
Naming.
Yeah, the names are kind of sus. Not gonna lie.
In every Lisp, man. I think the best I've seen is closure, which is a statement. Because you have functions like slurp, pit.
Yeah, I agree. Clojure, I really like Clojure's naming compared to other Lisps.
Yeah, common Lisp, man, it's crazy, the naming.
We have a problem, boys. We have a problem.
Hmm.
Do we have such function? Man.
Uh,
We could like that's so fucking dumb. But we could do well. We did split by already by our. Well, we didn't even make it. We copy pasted from Stack Overflow. We could make take up to, right, which takes, and this is not closure, so I need parentheses here. So we could make something like a list, at least L, for instance. Then we could make like an if. Actually, before the if, we're gonna make a let. Then we can pick the size of of such thing. So length, length. I don't know how to type. Thank you very much. L. Then we do an if. Then we can do if um, um, and if size. If the size is greater than n, then we're gonna do a normal take. So this means take ln. Otherwise, we're gonna make take l size, right? Which is like meh, to say the least. But okay. Oh, there is another take. Oh no, but this is not the take that we care. So this is take up to. Like
You can
I feel
blame
so. Go on.
you can blame the SRFI number 1 for this stupid behavior of take, because the justification they give for the legal value of I in that document is that if you append take xi and drop xi, you should get x, which is not necessarily the case if you allow I to be longer than the x length.
Yeah, I feel like every single time I complain about this with the Okemo fanboys, they always complain. Are you afraid of coding your own auxiliary functions because they
Which
like?
is a stupid argument. Like,
Yes. Are you afraid? Can't you code? Are you just like a dogmatic
yeah,
fanboy of
can't
Haskell?
you? I mean, that doesn't even reserve a response, to be very honest.
Like, and I am. No, no, no. I'm not saying that I like. I do like to believe, and I think we have a problem. I do like to believe that I know how to code, but I'm just saying that doesn't justify your standard library sucking. That doesn't mean that. But
The entire
doing stuff like this true makes me feel like okay, so this is how Okemo people feel. I understand.
the entire point of a library is to have reusable code, right?
Yes,
So
exactly.
your units of reuse should be convenient to reuse. It shouldn't be stupid like take not allowing you to pass a number
To take less
larger
argument.
than the minimum. Yeah.
Yes.
I think something
Uh,
is wrong. I do really think something is wrong.
Wait, is it still
by the
compiling?
way,
No, I
by
think
the
it's already
way,
finished
Lemos,
compiling. I think it's
Oh,
running.
it's running again. Okay.
by
Yeah,
the
but
way,
okay, it's
Lemos,
just stuck.
I just want to say your implementation of take is now linear on the length of the entire original list
No, yeah,
instead
I
of
know, I
just
know,
the
I
list
know,
you
I
are
know, I know.
building.
I completely know. Okay, we should definitely try to verify what the heck is going wrong. I think that this loop is now fucked. So let's try to print something in there. So I don't know, maybe here. Uh, hello infinite loop. Yeah. Oh yeah. I think the loop is
Um,
fucked. Okay, the thing that sucks is that I have no idea at all how to fix it. I have no idea.
can you print the index and the page bound at each iteration?
Sure. So you want the index. We don't really have. Oh, we have the index, yes. And then the print page bound. Yeah, the page bound. Um, okay, so what the heck is this?
Oh, right, right. You completely forgot that Racket has rational numbers.
All
But it
right,
doesn't make
that's true.
sense at all.
It does, because you are
Oh,
doing a
I mean,
division
like
to
other
compute that
Lisps as well,
value.
right?
I'm using what to compute the value?
A division, not an integer division, but a rational division. That's the problem.
Oh, okay. So what is the name? Div?
I think it's div.
Really? That was just a Haskell
I might
gamble.
finish. No, actually, it's not. Div is something I have in my head because it's a very nice name. It's actually quotient.
Oh man,
What? What?
quotient, like
Wow.
quotient, quotiente.
Okay.
Funny.
Okay,
Why
so
are
are
you
we...
surprised? That is the technical name of
Yeah, but
the.
it's
Yeah,
still
yeah,
really
but
fucking wrong. It doesn't make any
that's not the
sense.
thing we think of, right? When you say it.
Yeah.
And infinite hello loop.
Yeah, we have the index of 7 million, so this is definitely wrong.
Yes.
Why?
Uh,
I mean,
Why?
we
Why
kind of
is it?
stress test it, right? At this point. Uh, what the heck is
Why is
wrong
it
there?
7 million though?
no, I have no idea why it's 7 million.
Can you do a like a break? It's a loop. Man.
Okay, so we have a guess though. Definitely, this needs to be wrong because this is the next value of index. And what I'm
Yes.
doing here is basically picking, summing up the instances per page with index.
So
Should I be doing that?
I didn't understand how do you get out of this loop?
No, we never
What
got
happened?
out of this loop. We
No,
are
no,
looping
no.
this
But
from.
how should you get out with
Um,
the else,
Oh
right?
no, we should get out with this if.
Which
I see the problem. I think
I think I see the problem as
we're
well.
not we're not adding one at each step.
Yeah, we're not
We're
adding
adding
one at all.
an arbitrary number, which
let me see.
may in one go go from less than to greater than without ever being equal.
Yeah, so can you remind me what this does, Magita?
Okay, so that is basically okay. So that is going over the amount of pages you can have, seeing at a pace of how many instances can be present in this page, and naming each page for this whole thing. So it's actually bound with the amount of pages. So if you can have 64, it's gonna do at most 64
But it's
with
gonna
some
the
jumps.
step is instances per page, right?
Yes.
Okay, so this is correct then. This
So
math is correct.
basically
The
that is the
problem
amount of pages. The step is for the amount of page things you can pick in the page,
Okay, I have another
Demos,
guess.
which I'm a little
the problem
suspicious about, to be honest.
the problem is that the equal should be a less than, I think.
Less than.
Wait, man, is that right? I'm suspicious of that now. Because think of these lemons, like, if you have, like, can you go back to my code?
Yes.
I think this is wrong because think of this. I'm using the instances per page, which should be the amount of. Can you go down to the other function that calls
Yes.
this? So instances per page is the amount of things the amount of bytes you can have with an integer division of the instance size, right?
Oh, this
So
is
it
this
will.
isn't this isn't this isn't instances per page then. This is
So
like instance size per page.
yeah, but even that, like, think about this. That is what that is basically saying is I have this amount of pages, right? Sorry, I have this amount of bytes that I
Per
can
page,
store
in a page, in a
at
single
one
page.
page in a single page with this amount of instances, right?
Yes.
Without and probably it's gonna have some remainders, so we just pick the integer part,
Yes.
and then it goes up there, and then that uses that as the step
Yes.
for the page.
Yes.
But what I'm using to do the thing on the page bound is the amount of pages I can have. Is that correct?
Uh,
Because one is the measure of the amount of entities in the byte that I can have, and the other is the amount of pages. That
yeah,
is
what's really confusing is that this sounds like a page number. So like which page we are, 0, 1, 2, 3.
yes.
And this is
So
like the total amount. And what we are jumping through is actually like
Yeah, because my
lemmas.
thought was I should iterate and just pick the maximum, like I should pick the most I can get at once, right? That's what I was thinking. But then I made this, and then I was thinking, okay, so I would just jump uh, this amount of entities, but that's the page. That's not the
Yes.
entity.
Yeah, that sounds really wrong now. Really wrong.
Actually, there's another mistake. You should do. It shouldn't be instances per page and page bound. It should be you start with the initial page number,
Mm-hmm.
you step by the instance size, not the instances per page,
Yes.
and you stop at 1,000 because that's how large a page is.
Yes. So I
No,
should flip
wait,
this logic.
wait, I'm
Yeah,
confused. Can you repeat that,
basically what
Marin?
Marinho is saying, just to summarize what he said, I should go this by the uh by the bytes, not by the page.
By the page count.
Yes, because this is basically what I intended was to pick the bytes and separate them in the pages. But if I can, uh, and I think that's what that
Actually,
was the plan. If you go look at line, is it 322? Like line 22 shows there.
Yes, yes,
So I'm reading the page number times instance size.
yes.
So let's see if I have like four. Let's suppose that I have four and it only fits one. Uh, wait, let me see. If it's two per page, okay? Think about this scenario. So I have
Yeah,
four lines in the disk, and it fits two things in one page.
yes.
So what I would do is that I would have 64, and the F sharp 4, by the way, um, it would if the step is actually it would still fill the other pages with nothing, right? So that doesn't matter. So I would basically do start from 0 and then grab 2 on the next step. So the first thing would be 0 and it would be reading 2, right? And the next thing it would be 2 and then the page number is now 2 and then I go and multiply that by the instance size and then I grab the next 2. So I think this is right, but I misnamed it by page number. That's not a page number.
Okay, what's the name of that? What the name of that should be?
So that is the amount of how can I say? That's the amount of bytes that fit in a page. Like that's an offset I can jump to get the amount of bytes that will fit in a page. But then I get my then the question is, Marinho might know, what would be the page bound, Marinho?
uh,
Just for the record,
page
I
count.
didn't follow what Mageta said with the math because it
Oh, I think it should be the size of the chunk, right? Because that's the most I will read in this thing. And then if it's more, and then I should calculate beforehand with that amount to read, saying if the page bound, which I would call like, I don't know, amount to read or whatever, if that is more than which is the check that I do below. Okay, so man, this logic is wrong. We can go by. Yeah, I think I know why I didn't run into that problem, because since I put 8 kilobytes and I had way less than this on the disk, it was never using more than one page, right? So then this problem doesn't exist basically. So if I use 2, I think it would already fail.
Wait, can we go through again just real fast, but with the correct names? So instead of these three names, which names should we put to these
So
values?
instead of me giving you a name, let me try to explain you with summary up. Okay.
Sure.
What I'm assuming is that I'm jumping pages. To what's the purpose of this function? Tell me. It's to fill a page, right?
Is to fill, yeah,
With
each iteration of the loop fills a
yeah,
page
it's to fill a page with what? The indexes and the
and the
data, right? The
instances.
binary. So what makes sense for me to loop by? Like the a page offset, like a page iteration, like 1, 0, 1, 2, 3, or that I use to get the chunks. or the bytes because I'm getting I'm getting the amount of bytes that go in this
Shouldn't
page.
this be page size?
Yes. So that's the problem. This for is wrong actually.
Okay, so instead of instances per page, we should have a page size.
Something like that, yes.
We should have a page freaking fucking size.
And then you
So,
should have something like max page size, right? Which is the page bound.
okay, so then you're saying max page size. Is the initial page number correct still?
Yeah, that will still be 0.
Okay. So let me see
Well,
what
the
we're
first
doing. We
passage.
are we
The
are
first
starting from
passage.
0. Each
Hmm.
time, each iteration, we jump page size, and we want. So this is basically the amount. Yeah, this is the chunk size.
Yes.
I think I'm actually gonna use that chunk size.
Chunk, yeah, chunks.
Chunk
It's the
size.
only of one. Yes.
That makes more sense to me now. But wow, that was confusing as fuck. Uh,
Oh, that is
Can
yes.
we go back to that infinite loop real quick and change that equal to a less than?
yes, but I'm gonna first change replace string. So I changed the page bound to chunk size, and I also changed the instances per page to page size. Okay. And then you want to do what again? You
The
want to
less
change the
than
equal
the
to
take.
put a less
The,
than.
Yes.
Can you explain why?
Because unless the value that we are adding to the index exactly divides our maximum size, we're going
Mhm.
from a number that's less than the chunk size to a number that's greater and never passing through a number that's equal, which is why
Yeah,
the
I
loop.
think
But
yeah
so this
that
is a
might
thing
explain
that
the
this is a thing that probably these computation expressions does for you. It doesn't go
yeah that
over.
this in F sharp. Yes, it doesn't allow you to go overboard.
Okay, so let's see what happens now. We should have still a few prints, but not infinite for sure. We didn't have any print. That's
Are
sus.
we storing data?
Uh,
We
that's really sus.
Oh wait. If it's less than it, the first iteration we already get
Yeah,
out,
yeah. That
right?
that explains it. That
it
explains it.
should be it's backwards. It's backwards. It's backwards. Yeah.
Okay, so
Uh,
now it should be.
or equal, right?
Actually, actually, it should be. Let's do this the proper way, the way that is in that article that I linked a long time ago. It should be less than or equal to, and then you flip the order of the arguments.
Wait, it should be less than or equal to
I
this,
mean, we're going.
this.
Yeah.
Okay.
Wait, is that
Uh,
correct?
wait. What is the index now?
Yeah, I want a better name for this garbage. Because you called it page number, and I don't think that's
Yeah,
correct
that.
either.
Yeah, no, that is not. That is the size of bytes that you can take in the.
No, no,
Ah,
that is a page number actually. That is a page number because we are basically doing this. Let me explain. So let's suppose that you have this, and let's suppose that the page size is 3. So 3, 3, 3, and so on. So let's suppose that this happens. So you have the index is the index for 1, well, 0, right? So
yeah, but like
0.
the page number I thought was like it would be 0, then 4, right? In this case.
No, it's gonna be 2, then
No, yes, but
3.
if that is the case,
Oh,
it's
that's true.
wrong.
That's 4. That's 4.
Yeah,
Yes,
it's the
yes,
index where
yes.
the page starts, but that's what we
Let's say
want.
page offset.
Oh man,
Page
I hate using
offset.
offsets everywhere. But
Uh,
yeah,
let's
okay.
say page offset. So
How do I
index
do?
page offset. Cool, cool.
Yeah,
So
but now you probably renamed stuff that you didn't mean to.
I don't think so. I really don't think so.
Well, he selected the area. I think there's no problem.
Yeah. But I think I did some
I mean,
bullshit. Yeah, I did some bullshit.
Offset
line
is
line
Uh,
79.
yeah,
Line 79.
indexes. Yeah.
line 79.
Yeah, 83 as well, indexes.
Okay, so replace index space with
Well,
page offset
there are
space.
places without space, right?
It worked.
There are.
Oh yeah, this thing has parentheses. That's
Yes.
true. Page offset.
If you added the space, that means that you saw where you had an index. So why didn't you just
Index.
went there and modified?
Okay,
And
so
that's
it's correct.
why and that's
If it,
why I use Kakone, because I can see what I'm selecting before I edit.
that's not an argument because Emacs also allows you to do that. Not the function that I did. There
Yeah,
is
but
an
in
indexing.
Kakone, that's the default way to do it. Like, it's what you just do normally.
So this
You
is
don't
a
have to think
page
about it.
offset.
I'm sorry, but you have to be muted, Marinho. You're pitching this forbidden here.
Okay, page offset. So this is still wrong, right? Because you're basically asking if the... No, this is correct. This is correct, right, Marinho?
Uh-huh.
Because I swapped the arguments.
Yeah.
Which, in my opinion, is harder to read, but I'm gonna do it to please Marinho.
To me, that seems correct.
Unbound
If
identifier at line 71.
if you want to read it the other way around, if the page offset's less than the chunk size, you have to flip the arms of the if as well.
Oh, that's true. So never mind. So never mind. No, wait, what you said?
Like, if you want to do less than page offset chunk size, that's the natural way to write it because the chunk size is the upper bound, right?
Mm-hmm.
Yes.
But then you also have to flip the arms of the if because you are effectively inverting your
Oh yeah,
conditional.
it would be the else, would be the then.
Uh, there,
There, you found the parentheses
there.
then.
Well, I cheated, like, so because I have this, so I can cheat.
Yeah, yeah, but
Okay.
now you have to do the thing like to reorder the
Yeah, you now
conditional.
flip. Now
Wait,
Yeah,
flip to
remove the
greater.
equal and
that?
And
ah
then flip the page offset, right?
I'm confused. What Marinho wanted, man? I think we are just doing
no,
crazy stuff now.
you just have to, yeah, you have to page offset chunk size.
Oh no,
But
sorry.
now
It
you're
would be
doing
still less than, right? Less
you
equal.
just have
But then you
you have
flip
to be
the if
less
and else.
than you just yeah, but get rid of the equal. Get rid of the equal because otherwise,
Okay, so if the page offset is less than the chunk size, then we do the stuff. If the page offset is equal or greater than the chunk size, we just return.
Mm-hmm.
That
yes.
sounds correct. That sounds correct. And the last time it worked, please still works. That would be nice. Thank you very much. So we are printing something. We should evaluate if it makes sense before the halo.
Yes. And then
Which
I'll
is
do
really
the
hard
Halo
to
music.
define if it makes sense because we have like the ask number of the characters.
And
ah!
if it does work, I will do the
Just
Halo music. So don't worry.
just
So
just
C
do integer to
pointer.
char.
You can deserialize it, right?
Yes, we can deserialize it.
So that
Actually,
would
we should
make
not
Just
be
music.
using a list in this particular instance. We should be using a byte stream, a byte string. I
yeah.
don't actually remember why. That was an implementation detail that Magetta was exploiting, and for me to just pass through, I also exploited. In order to do byte string, we're gonna have to swap the something that Magetta did. Anyway, so let's
And
see if this makes sense. So the first thing that we put on a pager is the pages. We have two pages, I believe. This one and this one, right?
Right.
Then we have the two indexes. I have absolutely no idea if this makes any sense at all. What is the 120? Oh, this is these are the values actually. So let's go here. Yes, 123 and 100. Yes, 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 yes. Apparently it
But
works.
the order inside of the pair should be the other way around, no?
I
The
have no
key is on
idea.
the left.
No, the key is not on the left. The key is not on the left. I can tell you because it's in here. This is the key. This is the index, right? And this is the thing itself. If you want to swap, we just need to do page offset, which is then different than what Magenta did. Right? It's different than what Magenta did. But maybe I need to swap the car and the Kadar here. So what do we put first when we do an insertion of the tree, Magenta? We put the first the index and then the value?
But the index and then a
Yeah, b
value. It is
plus
the
3.
yeah, it is the value first, right?
I-
Because
I-
the value is the one that actually I don't know, depends on the the all the APIs.
no, but you know the API. You changed the
Yeah, check
code.
on my code. I don't know. I think I don't remember the order. I think it's the
Uh,
key and then the value, right?
okay, so it's the
Yeah,
key then
key
the
value.
value. Okay,
Yeah,
so
it's key
then
value and
I
the
need to
key
swap
in
the
this case,
Kadar and the car here.
Oh,
yeah,
okay. The key is actually the the key is actually the value of that column for that row, right?
yes, it's what the
So
user knows, right? The index is what
Oh,
the
okay, so
page is.
oh, okay, so then it is like this. Okay, let's assume that this is right. We can't check the 42 right now because we would have to count. Actually, I'm gonna send this to Marinho, and he always has Racket's repo open for some reason. Can you calculate the size of this for me, Marinho?
uh the size of this, where
It's
did
on the
you
chat. Like remove the parentheses and just count how many numbers we have. If we have 42
total?
numbers, yeah, total.
Okay.
Because as far as I
I
can
need to copy
tell,
that.
no, no, no. I need to check with
Uh,
Mageta if this math is correct. Mageta, correct me
Hmm.
if I'm wrong. If we have, um, yeah, if we have uh, this amount of, this is a page, and this is a page, is this always gonna be the amount that we already read?
this
Wait.
42.
It is 42, so it must be. Mageta, what I just asking, the answer needs to be yes. It needs to be. Uh, okay, so let's continue further because this seems to be correct. So now we're gonna do finally, the function that does search. Search, the famous function search. So what should we do to do a search? The code is not a lot, so we should have plenty. We should do this fast. So the first thing that Magenta is doing a lookup. So that means that I'm copy pasting this. Pretty much.
Amazing. Amazing.
Next up, what the heck do we put? Let's actually do this. What do we put in the thing? What are the parameters? So the first thing is a schema. Sure, I can give you the schema. We have an entity name.
Just a random comment Belani just sent me. I was defending Golang for him, right? And then and then I said one of my top career moments was when a big nerd justified moving the whole company to Golang because the binary was clean.
What?
That is weird.
Such an
What?
unexpected turn on events, man. Like what the heck?
Completely unexpected, man. Completely unexpected. So, key name is gonna be car of where clause. Then we have the
I don't
key,
get it.
where clause again. Um, this is done. This is done. Boom. Okay, now we have a problem because we don't have modeled this, but this is really easy to model. So let's do it. So this is gonna be copying this. So this is gonna be a projection request. And a projection request is basically composed out of two possible things, right? Fuck, what is the best way to model a sum type? Marinho, give me. Give me.
A sum type.
Yeah. What is the best way
No,
to model that?
Uh, you just
nulls are the same thing as nons, right?
no, actually,
I think
you
Commander
use
showed
him
us.
usually like if you just need nullary constructors, the easiest way is to just use symbols. If you need parameters, each tag in the sum type would be a different struct, and then the entire sum type is an OR of the predicates for all the
Okay,
cases,
so let's
basically.
not model this right now. We can think about this further. Let's always assume it's going to be a restrict for this
Yeah, I
particular
remember
implementation.
Commander showed us how to do a maybe in Common Lisp.
It's been a while, I
It
don't
was
remember
with the
anymore.
structures.
To do a maybe in scheme, you just either pass the value or the boolean false. That's just it.
Okay, let's always assume that, so then we can jump this pattern matching thingy. Okay, we also need something called the initial page number, which is 0. And we also need the amount already read, which is going to be 0 as well. Then we need to call build pagination. Build pagination gives us a pager. Then we do the prints that Magita is doing there. So let's actually do that. So this is already a let's start. So pager. So build pagination, and now we need the infinite amount of arguments. So scheme entity name. So scheme entity name. Attribute to index, initial page number. Uh, Attribute to index. Where are we getting that from? Oh, it's the key name. Okay, so it's the key name, the attribute to index. And we have initial page number and the amount already read. Initial page number, amount already read. That's gonna give us a pager. Cool. So what we do with the pager now? We do a try. So this is gonna probably return. So if um, equals -1. Do we need parentheses surrounding the -1? I don't think so, right?
No, because the parser will see that as a literal integer -1.
B plus. Now it's time for us to go here and put the find and get value in here. So we're gonna do exactly that. So find and get value. We're gonna pass the tree, so that means pager tree pager. We need to pass the key, so key, and we need to pass false for some random reason. So if this returns something -1, we need to do something about that. So let's just do a print for now. So did not find your thing, buddy. And then if we don't have a -1, that means that we have something. That means that we have something as an offset. So actually it would be kind of nice. So let's put search result, and let's grab this and put it in there. So search result. Otherwise, we're gonna do that indexing that Magita is doing there. So we're gonna get the pages out of the pager, right? So this let's do that. So pages. So this is gonna be pager, pages, pager. Then we're gonna grab the first page, which I don't remember what is the function in Racket. Does car works for lists, Marinho?
For lists, of course it does.
So I'm gonna get the first element, right, Marinho?
Yeah, car of a list is the first element of the list.
So car on pages, but this is we're gonna do another car again because no, actually we're gonna pick page uh, instances, and the return of this we're gonna grab the offset of it. So how to get how to do indexing on the list.
Uh, list ref.
List ref,
List,
yes.
actually, list ref gives you the value at that position.
Which
If you
is what
just
we
wanna do
want.
indexing, you need list tail, I think.
I don't get it. Why we don't want list ref? I think we really want list ref. Yeah, this jumps, list tail jumps a certain amount. That's not what we want.
Oh, right, because page instances is not right. That's actually after you deserialize it. So
Yeah.
list ref is correct.
So then we're gonna pick this search result. And that should be it, believe it or not. That should be kinda it. So what we can do now is this. Oops.
What about the actual table? Like there's an entity that's not defined anywhere inside of search.
There is an entity that is not defined anywhere. What do you mean?
Line 120, you're asking if the entity is a table, but what is an entity? It's not defined in this
Oh, I
code.
forgot the let. I freaking forgot the let. Yeah, actually that was missing. Okay, okay, so now we can go and swap search provide search. So what do I need to pass to that thing? I need to pass the entity name, the projection request, which for now is going to be a list of thingies. So let's say what are the thingies that we have? We have name and age. Oops. Let's see that these are our projection request. And we have the where clauses. Actually, this needs to be... That's weird. We're not using the projection request anywhere in the code.
Projection request.
Yes,
Wait,
because we
what?
are assuming that we
Oh yeah.
do in fact.
We are assuming what?
You didn't want to model it yet. So
Yeah, but that doesn't answer...
Yeah, we're
Oh,
just ignoring the all, right? It's just always the
no, but
restrict.
we are also we are ignoring this filter. That's basically what it means. So in that case, I'm gonna just remove it for now.
Yeah. We need to
So
modify. So I did that because I modified the language. So we added that on the parser.
the where clause is a cons. It's a cons of a key name and a key. So the key name is gonna be age, and the key is gonna be 1 because we are assuming equality. I have another question. I think we need to call the deserialization as well. I don't think you can jump this.
Well, yes, you need to. I mean, you don't, but
It
to
would be
get
kind of mad to not do
to
that.
see the result, yes, you need it.
So how am I doing that? This
It's the function that serializes a row, right? That's
yes,
all you
yes,
need.
but I think I was expecting to read values from disk. That's what we're gonna do. Okay, so this is getting so bad that I'm actually gonna have to start putting the things on lets because it's getting bad. So let's put the instances let's put the line that I need to copy paste there, so I can grab. Okay, so let's actually say first page. You are car of pages. Then we're gonna say instances, which is the page instances of the first page. Then we want to get out of the instances something. So we can put instances. And
Wait, but
then,
this serialization works on byte strings, right?
yes.
But you have a list of integers.
I think that means I'm gonna have to translate it back.
Yes. And it also means that I was correct
Oh, it's a
about
list of
using list
ASCII,
tail.
right?
Yes.
Actually, it's a list of bytes. Bytes singular, as in a number between 0 and
Uh,
255.
A byte. Okay, so a byte is just a representation that is an integer, right? But
yes.
it's just a
So
byte.
byte string racket.
I'm pretty sure you can do list to bytes.
Okay, let's gamble. So list bytes, and then after I
And
do
then
that, actually I'm
instead
gonna.
of list ref, you have to do a list tail, I think.
I don't. I still don't
Maybe.
think that's the case. I still don't think that's the case. So I'm gonna call this payload. Uh, yeah, I'm gonna call
Because the way
this
it's written
payload.
right now, it's gonna be a type error because you have a list of integers. You're doing a list ref, which returns an integer. Actually, an integer
No, this is not returning an
typically be.
integer. This is not
Why
returning
not?
an integer because we have multiple instances, which each one is a list. So we have multiple. We have a list of lists, and in the
Oh,
outer
I see, I
list we
see.
are grabbing the search. We are using the search result as an offset. I should actually put
Right,
these as
right,
like
right.
this is an index. This is actually an index. Then we transform this into that. So this now is a payload. And now I can grab this and put it in here. What is wrong with the let? That is wrong. No. That is also wrong. Yes. What? Oh, another parenthesis. Yes. Then we are missing the parenthesis of the if, the other parenthesis of the let, and then this closes it. Okay, so this is payload, and that should be it. Actually, that should be it.
We shall
So
see.
we're gonna get the the actual row deserialized that has the age equals 1, which will never gonna happen because nobody has that age. So let's pick Nathan. I put Nathan very old for some reason. Let's
I
see the errors. So I missed a parenthesis somewhere. That's cool. That's cool.
sinful. Use
So
the max check parents.
check
Parents. Check parents.
parents.
Yes. There. So yeah, it's down there.
Search results, so something went fundamentally wrong. That makes sense because I forgot to swap these to index. What else? What else? Imagine if it works. There's no way. Uh,
Okay,
age
It did.
editor
it did.
Nathan.
So it did work.
Wow, that was
Let me search.
fast.
What another ID?
Uh,
100. Search for Linus. Yeah, that is not very fast.
yeah. Yeah. Why
Well,
does my
Uh-huh.
Emacs have more bytes than Visual Studio Code's Nathan's Visual Studio Code?
Uh,
Yeah.
padding. Answer is padding.
yes.
Oh, that's the answer. That's the actual answer.
Oh, padding, right?
Yeah, padding. So these are let's see Nathan again. Yeah, Nathan had more. Wait, but
Written.
why Nathan only had this amount and I had a lot more? Oh, I
Oh,
had
it's
two
only
only. This is two.
yes, it's just true.
So
I
this
think we're
is
looking
like
at the index.
5 characters and Nathan has 6 characters. That makes sense. Okay, so it works, the search. Believe it or not. Amazing. Amazing. It freaking works. Let's try another table actually. I'm actually really curious. So let's change the table from that to car. Let's actually also, oops, wrong shortcut. Let's uncomment that. Let's uncomment that. We need to put some rows into that. So do I have anything about that? I have absolutely
So
nothing about it. Okay, so let's copy
And we
this.
are way beyond the time for the stream.
Yeah,
I think
we
we
are 30
should
minutes
just
after.
stop recording.
Okay, let's start because we actually finished the goal of the day, which is to finally
Yes.
have the naive version of
And I
search.
want to do something in Erlang. So